Hello, everyone. Thanks for being here today. My name is Philipp. I'm with David Escaramuzza's lab. And as you might have heard, we work on drone racing. And we consider drone racing one of the main milestones for mobile aerial robots. But why do we even care about drones? There are pretty awesome other autonomous vehicles around, right? For example, there is Tesla and autonomous driving that is already super useful today. Autonomous driving exploits a structured 2D environment. And in autonomous driving, we can carry a lot of sensors that help us. Furthermore, driving mainly happens on the ground, right? So in case of a failure, a driving system on the ground can be stabilized. We can brake, stop, and wait for the user. Then we have lagged robots, which have an extremely high potential because they can navigate even unstructured and like 2.5D environments. And they can also carry a lot of sensors. Lagged robots also are mainly on the ground and can be stabilized in case of failure. For example, probably by laying down and just waiting until a user can fix a problem. However, we want to work on drones because drones are extremely dexterous and nimble. Drones can navigate unstructured 3D environments, so they can literally go anywhere. However, drones have strict constraints on sensor and batteries due to their size and weight limits. They often can carry only simple sensors like GPS, cameras, and IMUs. And drones, as they are an aerial vehicle, have an extreme downside to them. They can fall. They are an extremely unstable system, and they need state estimation, control, and planning to always work robustly for safe operation. So we choose drones not because they're easy, but because they're hard. And we choose drone racing specifically because it can provoke some of the robustness problems drones face nowadays. Drone racing, as you see here on the little videos on the right, can happen in various environments. We face challenges in drone racing that have mainly to do with, for example, sensing and also control. On the terms of sensing, we have motion blur that makes state estimation using cameras pretty difficult. We have flight in indoor environments where GPS is not available. And we have problems with high dynamic range, for example, in an environment as you see on the bottom where we have lights in a dark place, or even just if we fly through a forest. Furthermore, if we go at high speeds, there is an insane amount of sensor noise. And we need high fidelity modeling to capture all the effects that impact the drone. For example, also complex aerodynamics. Drone racing is pretty relevant to the field in terms of robustness because we see parallels to applications such as package delivery, where we want to go fast and deliver a large amount of packages. We have inspection, flying taxis, where robustness is a very important point, and also search and rescue missions, where time is actually a critical factor. Therefore, for us, drone racing is a little bit a robotics milestone. It's our next moonshot. So when we do drone racing, we typically have to do estimation, planning, and control. And most of the time, actually, estimation fails first. We are heavily working on this topic, and estimation for us is something that is still work in progress, but we also do a lot of progress. For the task of drone racing, we want to abstract the problem a little bit and help our drones. So we use a motion capture system to replace the estimation and be able to push the limits further than what we can do today to be prepared for tomorrow. Planning is a big unknown when it comes to drone racing. It seems simple, but actually, do you know how we can even go fast? Are humans the best baseline? What is even the fastest trajectory in drone racing? And finally, once we have a fast trajectory, control becomes very challenging because we have uncertainties and unmodeled effects like the aerodynamics. Today, I want to focus on some recent progress we did on the planning part. In fact, I'm going to dive into one of our recent publications to Science Robotics just from this summer on time optimal planning for quadrature waypoint flight. So going as fast as possible from through multiple waypoints. To give you a visual overview what this looks like, let's first start with what we want to reach. These are two expert human pilots flying on a track that another expert designed. They fly extremely fast trajectories, reaching speeds beyond 70 kilometers an hour indoors. They exploit the drone dynamics and race each other. This is what we want to ultimately reach or even beat. What we achieved is actually superhuman performance. So this is now our autonomous drone, not a piloted drone. We came up with an approach that can plan trajectories, and we execute those trajectories in a motion capture system faster than any human could ever fly. Actually, this made quite some news. It was covered by a lot of media outlets, even Forbes, where our AI-controlled drone racer has beaten human pilots for the first time. How we do it is by essentially generating trajectories that are time optimal in advance. So we pre-compute trajectories and then execute them in our motion capture system. Time optimal planning for quadrotos is hard. Quadrotos are a difficult system. They have complex dynamics and actuator constraints. There are a number of available state-of-the-art methods to generate trajectories. For example, sampling-based method. However, if we need to explore the state space and the input space of a quadrotor, the sampling complexity explodes, and these methods can no longer be applied. There is dynamic programming. However, it relies on some facts. Like we need to get global optimality, we need sections that are locally optimal and connect them. And if we have complex dynamics, that's not easy. That's actually very difficult, and dynamic programming becomes difficult to apply. We have bang-bang approximations that can compute time-optimal trajectories, for example, for a point mass model in no time at all. However, these do not apply for a quad, since a quad has continuous rotational dynamics that impact the acceleration dynamics. So bang-bang approximations are unfeasible for quadrotos. Finally, we have the popular approach of exploiting differential flatness properties of a quadrotor and using polynomials to describe trajectories. However, unfortunately, polynomials are suboptimal for the goal of time-optimal planning. They only work very well in state-to-state conditions, and they make it hard to apply the platform's constraints. So why are polynomial trajectories suboptimal? If we look at the polynomial, it describes decoupled x's. These are insanely efficient to plan, but they make it hard to apply input limits. Furthermore, one advantage of polynomials is that they are smooth. So they can exploit differential flatness and render feasible trajectories. However, being smooth as a polynomial also means that we can reach peaks only in a single time instance. So over a polynomial, we cannot reach peaks multiple times or for consecutive durations. However, what we want in drone racing is to be always at the limit. So we want to reach the peaks of our actuators always or as much as possible. So we resorted to discretized trajectory formulations, which can be computed using trajectory optimization. Discretized trajectory formulations allow to include system dynamics, apply the correct input limits, fly through multiple waypoints, but for this we need to allocate waypoints to discrete nodes or times along the trajectory. This is a problem because we don't know these times in advance. And what we came up with is, instead of allocating these waypoints to nodes, we formulate a measure of progress, which is only allowed to change in proximity of a waypoint. So this allows to simultaneously optimize the trajectory and the waypoint time allocation. So when we pass each individual waypoint, we can solve that all in one problem. How do we do this exactly? So if we look at the discretized trajectory, we can let this go through multiple waypoints. For example, we have here 2 waypoints that we would like to pass. And we would like to pass these waypoints within a certain volume or a certain tolerance. To do this, we formulate our measure of progress, our lambda variables. Actually, we don't formulate only one, but one for each waypoint along the whole trajectory. Our problem is specified by the progress variables being incomplete at the beginning, which is for us equal to 1, and complete at the end, which is equal to 0. So remember, we have a progress variable, which is incomplete at the beginning at 1 and complete at 0 in the end. We have an evolution of progress, which tells us how the progress changes over time or along the trajectory. And this evolution of progress is the essential part which we are now going to exploit to make our trajectories pass through both waypoints without us having to tell the optimization when to pass the waypoints. To do this, we can look at the connection between a waypoint and a point along our trajectory. Like here, we compare the x2 node along our trajectory to waypoint 2. What we essentially want is going through the tolerance sphere of this waypoint. And to do this, we formulate a complementary progress constraint. This constraint basically means that on the right-hand side over here, we have a comparison of the distance between our waypoint and our trajectory node. And on the left-hand side over here, we have our evolution of progress. Now notice that these two factors must always equal 0. So one of those factors must be 0. Either we need to be able to bring our distance together with some slack tolerance to 0, or our evolution of progress has to be 0. So in this case, between waypoint 2 and node 2, our distance measure is non-zero, and therefore our progress must be 0. This means at the node 2 along the trajectory, we cannot tick off our waypoint 2 as completed. Now let's look at another node, this node 8, which lies within the tolerance. In here, we can bring our distance measure minus the tolerance slack variable to 0. And therefore, our progress or our evolution of progress can be non-zero, meaning it goes to 1 and it marks our waypoint as completed for fulfilling the constraint at the end and at the beginning. We do this obviously for all progress variables along the trajectory. So for progress variable 1, it is being ticked off at waypoint 3, and after that is marked as completed with the white circles here. And for waypoint 2, we tick it off at the node 9, it being completed after that. This leads to a novel problem formulation with which we can compute those trajectories that we shown you before. We can fly those in a motion capture system and achieve superhuman performance. We do this with numerical trajectory optimization that starts from an initial guess and can come up with trajectories that are faster than humans. In conclusion, we have shown that computing time-optimal trajectories for drones is in fact possible. The resulting trajectories can be executed, so they are feasible, fulfilling the drone's dynamics and actuator constraints. They can beat human pilots. They are faster and more robust than human. We can see this on the lower right-hand side plot, where human experts reach larger lap times, and larger variance than our time-optimal trajectories, shown here. These trajectories can now be used for other approaches, for example, for model predictive control, or even neural networks that can learn how to fly such super fast trajectories. And our approach can be used as a baseline for such other approaches. However, our time-optimal trajectories cannot yet be verified to be global optimal, because we are solving a non-convex optimization problem where it's really hard to establish any guarantees for. Having said that, we have not yet found a counterexample. We have never seen a human flying faster. We have not yet seen networks or sampling-based approaches coming up with faster trajectories. Another disadvantage of our approach is actually that computation of these trajectories can take hours. Typically, it's within the range of 30 minutes to 1 hour. But this already means that we cannot regenerate trajectories on the fly. And this is a problem because we don't always have this nice motion capture environment, which is static, but we actually want to deploy our algorithms out in the wild. So to do this, we have some ongoing work from one of my colleagues, Angel Romero. This is a quick outlook to his work on model predictive contouring control. In this approach, we basically work in a receding horizon fashion. What we do is we can solve a similar problem, but using MPC. So we can online adapt our flight strategy, and we also optimize a path progress. In this case, we formulate an arbitrary reference, an analytical reference, which is path length parameterized. Then the MPC does not only optimize the system model predictions, but also the path progress it does in every step of the prediction. This means that we can dynamically adapt to the platform limits. So we can still fulfill actuated constraints, or for example, a velocity constraint, but within those constraints, we can go as fast along an analytical reference as possible. This means that we can do this online without the need for pre-computation, and we can adapt to changes, for example, a changing environment or even opponents on the track. You can find this work as model predictive contouring control for near-time optimal control to flight already now on arXiv, and it is under review for TRO. And with this, I want to thank you very much for your attention, and I'm open to questions.